Our first speaker is Karine Chemla, and please.
Before I begin, I have to thank my chair for having been the best chair ever. Thank you so much. And thanks also to the organizers for this conference, which is really great and that I'm happy to be able to attend. So the question is philosophy useful for science? As a historian, I will argue that philosophy has been useful for science by discussing an episode in which, in my view, this has been the case. This episode is not about a philosopher making a contribution to science or taking part in a scientific work. Rather, it is the case of mathematicians achieving a huge breakthrough, thanks notably to the philosophical inquiry they carried out to fulfill the mathematical program on which they were working. In other words, it is a case of entanglement between mathematics and philosophical reflections in mathematicians' work that proved quite fruitful. I'm thus quite happy you arrive at the right minute. I'm thus quite happy to learn of the teaching program at Chapman, because I really think it's going to be very important to train mathematicians and physicists in philosophy and the other combinations I'll let you do. Two notes before I begin. I will speak about mathematics, and I'm aware that in this room, not everybody is a mathematician. So I will try to explain some mathematics with the hands, and I ask for the specialists to be patient with me, to bear with me when I'm doing this. Second, as you will see, my slides will have many quotations from original sources, translated quotations. These quotations are pieces of evidence on which, as a historian, I rely. Except in a few cases, I'm not going to read them extensively, but this is a way for me to display that which underlies the claims I put forward. So the breakthrough in mathematics on which I will focus is the introduction by Ernst Eduard Kummer in a letter of October 1845, the introduction of what he called ideal prime factors of a complex number. So what he means by complex number is not what we usually mean by complex numbers. First, technical parenthesis that I will close very shortly. For him, a complex number is made with alpha and an nth root of 1, with which he creates linear combination with integral coefficients. So a complex number for Kummer is a number of the form f of alpha of the form a plus a1 alpha plus a2 alpha square and so on. And what he means by prime, you remember, among integers, 3 is a prime, and because it is divided only by himself and by 1. And the property that on which Kummer will focus, the property of prime number, is the property that if 3, a prime number, divides 12, which is 2 times 6, it means that 3 divides one of either 2 or 6. In this case, 3 divides 6. This is the property of prime number that Kummer will attempt to emulate with these numbers. I forgot to signal the end of the technical part. I hope that the notion of prime has been made clear for everybody. So the intention of Kummer is to make with these complex numbers the same kind of divisibility laws as we have with integers 1, 2, 3, 4, 5, and so on. Okay, so the first thesis for which I argue is that Kummer's introduction of what he called ideal prime factors in number theory, this introduction was inspired by both Jean-Victor Poncelet's introduction of ideal elements into geometry and Michel Charles' reconceptualization of Poncelet's ideal elements in geometry. In any event, this is where the term ideal comes from, as I will show shortly. This is a thesis for which I have argued in a previous seminar in Orange County. I will say a few words about it, but the main point of my talk today will be my second thesis, namely that the introduction of ideal elements in geometry derived notably from philosophical reflections Poncelet developed in the process of shaping a new geometry. And it is the outcome of these philosophical reflections that on the one hand led him to introduce ideal elements in geometry, and on the other hand, circulated as such and played a part in the advancement of other domains, including Kummer's major innovation in the context of number theory. So you see, this is a very interesting case in which the philosophical reflection helps to advance geometry and is picked up by someone working in a completely different field and helps him advance this other field, number theory. So first, let me very briefly outline why I claim that Kummer drew inspiration from geometry for his key idea of introducing ideal prime numbers. The first text he publishes about this issue is a report communicated to the Berlin Academy in March 1846, and I will very briefly take you through this report. I have succeeded, he claims, to complete and simplify two values that are very interesting. The theory of complex numbers, I skip, we have discussed what these complex numbers are. And I did this by introducing a specific type of imaginary divisors. Look at the term imaginary, that he immediately discards to say, which I call ideal complex numbers, and so on. So first, the first term that comes to him is imaginary, which he discards to introduce the term ideal. And also notes something very interesting, that there is at the time no ideal number per se, but ideal numbers are only relational, in a relation of divisibility to actual numbers. This will change later, but at the time, this is what it is. And why does he introduce ideal numbers? He explains there is a problem because these numbers, either they can be decomposed, like 12 equals 2 times 2 times 3. These numbers, they can be decomposed with elements of the same type, and then the number is composite. But there are cases in which a number of this kind cannot be decomposed, and yet he doesn't have the true nature of a prime number, because it lacks precisely the property I have described a moment ago, namely that if I multiply 2 by 3, I can only divide 6 by 2 and 3. And this is not the case with these numbers. So despite the fact that they cannot be decomposed, they still have the nature of composite numbers. And what Kummer does is that in addition to actual possible factors, he introduces ideal factors that decompose further and with which he is going to obtain the key property of prime numbers. So he's making comparison. This is the same thing as this and that. He's making comparisons that we find very natural. But there is one parallel that he makes that has remained unnoticed. And this is to achieve now a lasting definition of the true, look at this true, usually ideal prime factors of the complex numbers. It was necessary to find out the properties of the prime factors, so prime factors that could be either ideal or actual. These are the two terms with which I will refer to these factors, actual or ideal. To find out properties of these numbers that would persist in all circumstances. He wants a property that can apply independently of the contingency of whether the actual decomposition takes place with actual factors or not, more or less, and this is where we reach geometry, more or less precisely like when in geometry, one speaks of the common chord to two circles, also when the circles do not intersect. One looks for an actual definition of the ideal, again, the same term, ideal, but in geometry, the ideal common chord that fits for all situations of the circles. So we see that there is the same term ideal in both contexts. So ideal common chord immediately calls up the name of Jean-Victor Poncelet, who introduced ideal elements in geometry, and in particular, precisely, ideal common chords. So I've taken a picture from the Traité des propriétés projectives des figures. This is the founding treatise for projective geometry. At the time, we do not have projective geometry, but only projective properties. I've taken a photo. These are not circles, but ellipses, but the definition of common chord is the same. You see here that the two ellipses intersect in 2 points K and L, and hence we can draw either a full line that will be a common secant, the secant cutting, so the line cuts both ellipses, and the segment KL is a chord, a line that goes from one point on the circumference to the other point in the circumference. It's a chord, and this KL, when the two circles of the two ellipses intersect, is the common chord. However, Poncelet, in the case when the ellipses do not meet, as is the case here, will introduce, as we will see in a moment, an ideal secant as well as an ideal common chord. So you see that Kummer is referring exactly to the situation of the common chord, whether the circles intersect or do not intersect, and Poncelet looks for a single definition in both cases. We see a value, an epistemological value, the value of the uniformity of treatment that will be as important for Poncelet as it is for Kummer, who looks for a single definition for all factors. So the question is, what are ideal elements for Poncelet? And before I begin explaining to you what are ideal elements in geometry for Poncelet, I think it's important to tell you what they are not. Because in the literature, we have, in general, extremely problematic descriptions of what ideal elements are in geometry. And if we want to understand Kummer's inspiration, we need to understand where it starts from. So there are widespread and wrong ideas on the issue of what ideal elements are. And to illustrate these widespread ideas, I will turn to David Hilbert. Okay, he's someone who made the claims that are wrong about ideal elements if we want to understand Poncelet. I'm not saying anything about ideal elements for Hilbert, but if we want to understand Poncelet, we cannot rely on Hilbert. And this will illustrate what is very, very, very widespread in the literature. So it's in particular, he goes back to this issue in other texts, but it's in particular in an article titled On the Infinite that Hilbert mentions ideas about what he calls the method of the ideal elements. So he wants to introduce an interpretation, a conception of the notion of infinity, and he will do this using the, I quote, extraordinarily important and fruitful method of ideal elements. So in mathematics, the first illustration of this method that he gives is the introduction of points at infinity for lines that are parallel and they would intersect at point of infinity. So in elementary plane geometry, we have on the one hand the points of the plane that are the only actually existent objects on the one hand. But if through 2 points we have a single line, 2 lines in general intersect, but parallel lines do not intersect. And we restore uniformity in the fact that 2 lines always intersect by introducing points at infinity. I quote, it is well known that by introducing ideal elements, there is points at infinity and a straight line at infinity, we can make the theorem that 2 straight lines always intersect at one and only one point come out universally valid. So first example of ideal elements he gives, points at infinity. He also gives as another example complex imaginary magnitude of algebra, the numbers that are such that when one multiplies these numbers by themselves, one can get a negative number, the square can be negative. And this is where he turns to this is where he turns to the issue of infinity. Just as in geometry, infinitely many straight lines, that is, those parallel to each other, are used to define an ideal point. So in higher arithmetic, certain systems of infinitely many numbers are grouped together to define an arithmetic ideal. This application of the principle of ideal elements is the most ingenious of all. So you see that here, interestingly, he's making a parallel between points at infinity, relating them to an infinite number of lines that meet at this point, with arithmetic, and he doesn't speak of Kummer's ideal numbers, but he speaks, in fact, of Dedekind's later rewriting in the form of sets of numbers instead of ideal divisors. And it's because they both use infinite to define ideals that he compares them. So what he refers to as ideal is not what Kummer referred to as ideal. Yet it's interesting that there is still the echo of a parallel between geometry and arithmetic and number theory. And then to summarize about geometry, for Hilbert, ideal elements would be points at infinity and imaginary entity. So it's a very widespread idea. We find it all over the place in the literature, but this is not at all what Poncelet means in 1822 when he speaks of ideal element. And this is not at all either what Kumar speaks about. So I will now turn to Jean-Victor Poncelet, about whom I have the pleasure to have a joint project with Bruno Bellos, who is in the room, and to his introduction of ideal elements in geometry. So what is the context of this introduction? Poncelet, like many people in his generation and in the previous generation, is impressed with the power of what he refers to as analysis, as algebraic analysis, as a term. You can understand he's impressed by the power of computation when one deals with geometry. When one uses computation, when one uses analysis, one can achieve results that are extremely general, and yet when one proceeds through geometrical means, one cannot achieve the same generality. And so in this book, the project that Poncelet presents is changing geometry, defining means in geometry that would make geometry different and that would make geometry able to vie with analysis, to be as powerful as generality. In particular, he wants to define means to achieve generality in geometry. So for this, he introduces two main principles. One, we think about it immediately when we think of projective geometry. Poncelet says, if we are able to determine properties that are invariant, not invariant, but that remain valid by projection, if we are able to find properties that we know are valid by projection, then we only need to prove them on a particular situation, and we can claim them for any situation that would be derived by projection. So this is one way of moving from the particular to the general. These are the famous projective properties that will become later on projective geometry. But there is another principle which is infinitely more important and infinitely more difficult to understand, as you will shortly see. It is the principle that is usually called the principle of continuity. So this principle basically addresses the issue of if computation, to put it simply, applied to geometry is so powerful, this derives from the fact that when we use computation, we can treat as same figures that the ordinary geometry would treat as different and would require different proof for each figure. So somehow this works, this power of computation in geometry works because these different geometrical figures are treated as same. And hence the issue is how to modify the geometrical approach to figures to secure similar properties in geometry. So central to the principle of continuity, there is a rethinking of the figure. So he considers an arbitrary figure in a position that is general, and he says in a certain sense indeterminate, among those that the figure could take without violating the laws, the conditions, and the link that persists between the various parts of the system. This last sentence is very difficult to interpret, but perhaps on our way, we will find means of interpreting this sentence, what he means exactly by this sentence. So we have a figure, which is, as we see here in the final part of the quotation, composed of various parts. It's a system that is composed of various parts. So we no longer have a particular figure that illustrates any figure, but we have parts. And the first example, it's again a figure taken from the 1822 treatise. I will analyze this figure bit by bit. So to begin with, please simply look on this figure and look at the ellipse, which is the system on this figure is composed of an ellipse and a line. And in fact, the position between these parts is indeterminate in the sense that we could have the line here, where we see that it intersects in our sense the ellipse, and we could have the line here. Don't pay attention to what is to this curve to which I return. We could have the line here, and here it would not, in our sense, intersect the ellipse. So if we were applying computation to geometry, there would not be any difference between the line cuts or the line does not cut. This is the power of computation. And Poncelet begins by not willing to distinguish between the fact that this line may cut or does not cut the ellipse. So the first thing that is central to his approach is the idea that we think of figures are parts that have indeterminate position with respect to each other. But there is a second aspect that is central in Poncelet's geometrical approach to a figure, and this is the link that is established between the positions of the different positions of the parts, and thus the link that is established between properties of states of the figure in this position. And this he does by introducing what he called a continuous motion. This is the first meaning of continuity in principle of continuity, but a motion through which relations will remain valid, will continue to apply. And I find it extremely interesting that the famous principle of continuity that is regularly mentioned, if we look at its full name, it is principle or law of continuity of mathematical relations of the abstract and figurate magnitudes. So the continuity applies, as we will see immediately, to the motion of the line with respect to the conic. This is the continuous motion, but it also applies to the continuity of the mathematical relations. So suppose this is the principle, one found one or several relations of properties, either metrical or descriptive. Metrical meaning we measure and we establish relationship between measures. Descriptive, simply things that meet with each other and about which we find a property that belongs to the figure. And we do this using the ordinary explicit reason. For the case of the conic and the line, we do this when the line cuts the conic, and we can make a reasoning that nowhere will introduce anything that is not seen on the figure. If, keeping to the same data, one makes the figure vary by imperceptible degrees, this is the continuity of the motion, or one applies to some parts of this figure a continuous motion, in fact arbitrary, is it not obvious that the properties and relations that one found for the first system for instance, the line cutting the ellipse, will remain valid, continue to apply another meaning of continuity to the successive states of the system, if, however, one pays attention to the changes that might have occurred, like when some magnitudes will have vanished, changed direction or sign, and so on. Just to explain a very easy application of this principle of continuity, we will state, because we move the line Mn continuously until the line M prime, N prime, we will continue to state that the intersection between the ellipse and the line has 2 points, in this case, imaginary. They have vanished, but they remain 2. We will continue to state that the chord cut by the line Mn in the ellipse continues to exist, and that it continues to satisfy the same relation. I've not written the relation, we are not interested in concrete relation, that Mn enjoys with respect, that Mn enjoys. And this is where Poncelet draws this other conic, which he calls the supplementary conic, which is the conic that will feature chords that enjoy the same metrical property as the chords here. So this conic, the supplementary conic, is a conic that is added to make this chord that is based on 2 points, M prime and N prime, that are imaginary. Okay, these 2 points, M prime and N prime, are imaginary, and he draws the distance, M prime, N prime, that continues to satisfy the same relation as the distance here. So we begin to see, just to begin, that this figure is not ordinary. We have points that represent imaginary point. Represent is not the right term. We have points that stand for imaginary points. We have lines that illustrate things that are imaginary, and so on. And something central in the analysis of this figure will be the fact that for this ellipse, if we choose a direction, the direction of the line, for instance, we have chosen the direction of the line Mn, there is a conjugate line, I will call it conjugate line AB, that is such that any chord that a line parallel to Mn would cut in the conic. So we have the chord PR if the line was there, we have the chord DE if the line was there, we have the chord Mn. Any line is cut by this conjugate line into halves. So we have this diameter line that will play a key role in analyzing this figure. Indeed, if I consider the chord Mn and I draw tangents to the ellipse through M and N, these tangents will meet in a point O prime that is also on this conjugate line. And it so happens that we have a relationship. We have a relationship between AB, the way in which the conjugate line cuts the conic, or the way in which the point in which, I'm sorry, Mn cuts the diagonal, the conjugate line, and O prime, the point at which the point at which O prime, the point at which the tangents at M and N meet. And the fact is that we have this relation and harmonic ratio. It's not important that we focus on it, but we have a relation between these points A, O, B, O prime. Now, Poncelet remarks that if we start from O prime and we draw the tangents, we immediately find the point O that is the middle point of this chord. So in fact, if one starts from O, one has M and N and one gets O prime. And if one draws, if one starts from O prime, one draws the tangent and one finds O. Or we could begin with the line MN, we would have the point O, and we would get O prime and the line M prime, O prime. So there is a kernel in this figure. There is a kernel about which Poncelet says that these points, O and O prime, can be constructed independently from the points M, N, and they subsist in all possible cases. So whether M prime and N prime are imaginary points or real points, we do not care. We can always, once we have the direction of the line MN or M prime, N prime, we can always construct this point. So the key point is that we have reached a major point, even though that seems absolutely obvious. Even though O prime is the middle point of an imaginary line, this point is real. So we have points that are real and we have elements that are real, even though they contain imaginary elements, even though they are related to the ellipse through imaginary elements. So Poncelet insists, since these points subsist independently from the reality or the non-reality of the points M, N, or M prime, N prime, there is no reason to neglect them in one case or the other. So whether it's the middle point of an imaginary chord or the middle point of a real chord, in fact, they have the same reality because we can obtain them as a property of the figure that does not depend on imaginary stuff. And nor should the line M prime, N prime be neglected when it becomes exterior, because this line, as we have seen, maintains relationship with the ellipse. It looks as if it was outside the ellipse, and no, it maintains relationship even though it goes through imaginary points. And this is where we reach the crux, because Poncelet first turns to names, assuming that we do not wish to create new names to designate the line Mn, whether it is in the position Mn or in the position M prime and prime. We persist in considering it as a secant of the curve when it ceases to meet the curve. So we are going to introduce the name of secant for any line, whether it cuts in real points or doesn't cut in real points. And here is the key point. We will say, in order to preserve the analogy between ideas and language, that its point of intersection with the curve, namely here, M prime and N prime, its point of intersection with the curve, and consequently the corresponding chord M prime, N prime, are imaginary. So we have the representation or the trace of imaginary objects on the figure, and that the secant is itself an ideal secant. And why is there this distinction, this key distinction that Kumar will pick up? Why is there this key distinction between imaginary line and ideal line? It's because we have seen that once we have a prime, we can construct the line M prime, N prime. It goes through imaginary point, but we can construct it. So for this kind of elements, Poncelet will use ideal. And he wants to distinguish such objects from entirely non-constructible straight line in path and direction. If by motion, I see that a line becomes imaginary, but I have no idea about its direction. I have no idea about a real point through which it would go. I cannot construct. This line is completely non-constructible, and he keeps the term imaginary for such lines, whereas he introduces the term ideal for elements that can be constructed even though they involve imaginary things. We will see a bit more shortly, but I want to return to this statement by Kummer, for which you have the German here. More or less precisely, these ideal divisors, well, more or less precisely like when in geometry, one speaks of common chord to two circles, even when the two circles do not intersect. So in this case too, Kummer can construct ideal elements that will have an imaginary relation with the actual number they divide, but he can construct them. He can find the definition that will cover them. So more generally, Poncelet returns to the contrast between imaginary and ideal. In general, we could designate with the adjective imaginary an object that from absolute and real that it was in a given figure, the line MN, would have become entirely impossible or inconstructible in the correlative figure, the one that is supposed to derive by continuous motion. So you see this central idea of a set of figures that are related by the continuous motion. And the epithet, and you will note that the epithet is exactly what Kummer uses. Kummer has the same philosophy of language as Poncelet here. We have divisors and ideal divisors. For Poncelet, we have second and ideal second. So the epithet ideal would serve to designate the specific mode of existence of an object, which, while remaining real in the transformation of the primitive diagram, the fact that I move Mn to M prime, N prime continuously, would nevertheless cease to depend in an absolute and real manner on other objects which define it graphically, because these objects would have become imaginary. If you want, M prime and M prime stand for imaginary points. If they were points of intersection of this line with the conic, they should be on this conic. So they stand there as imaginary point. This line is a real line. So this line is a second because it intersects the conics in imaginary points. So we have a real second and a real ellipse, but the relationship between the two, that are the 2 points M prime and N prime, are imaginary. This is Poncelet's meaning for ideal. And he states, since just as one already has in geometry names to express the various modes of existence that one wants to compare, like infinitely small, infinitely large, one must also have names to express those of non-existence, in order to give accuracy and precision to the language of geometric reasoning. So, to summarize what was said in the previous slides, we have two modes of non-existence, imaginary and ideal, and two modes of existence mentioned here, infinitely small and infinitely large. This is quite important because these ideas of ideality seem to have been introduced by Poncelet in 1820. This opposition between ideal and imaginary. But he did not use these terms in the same way before 1820. I will focus simply on a notebook he published at the end of his life. I'm sorry, I forgot to say that at the end of his life, he published lots of the manuscripts that led him to maturing his ideas that he presented in the treatise. So we have two books of published manuscripts on which we are working with Bruno. And I will simply focus on the fourth notebook that he wrote during the winter 1818-1819, and which is titled Philosophical and Technical Consideration on the Principle of Continuity in the Laws of Geometry. Technical for Jean-Michel. The use, he writes, and routine of algebraic analysis have introduced certain expressions which recall and characterize beings of non-existence. When we compute, we don't care what the computation means. We compute, and at the end, we interpret the result. It so happens that sometimes we go through things that refer to nothing, that have no existence. This is how, Poncelet continues, the infinitely large and infinitely small, whose existence is purely hypothetical, have already been introduced into geometry. I draw your attention to the fact that here he refers to infinitely large and infinitely small as beings of non-existence, which is different from what we have seen in the statements of the 1822 treatise. 4. He writes in 1818, 1819, when we admit, for instance, that two parallel straight lines meet at infinity, we ideally give an indefinite existence to their common point of intersection. So you see here, interestingly, that ideally has nothing to do with the 1822 use of ideal, but this is how Hilbert understands ideal. But this is the old Poncelet, not the new Poncelet. So we ideally give to the point at infinity an indefinite existence. On the other hand, the word infinite recalls the geometric non-existence of the object. It indicates the assumed existence is purely ideal. Again, this use of ideal has nothing to do with what we have seen for 1822. Again, in the fourth notebook, when he analyzes the 2 points have become imaginary, he asserts that the expression is introduced to maintain for these points an existence of sign, at least ideal. Again, ideal is used as Hilbert would use it, but not as the later Poncelet we use it. Hence, we see that we have a major transformation between 1818, 1819, and 1820. We have a major transformation with respect to how he understands ideal and how he understands mode of existence. Now, what is really striking, and this is where I can assert that this derives from Poncelet's philosophical reflection, what is striking is that this transformation appears to correspond to the fulfillment of a program in metaphysics that a few pages later, Poncelet puts forward. Just as one has names to express the various modes of existence that one wants to compare, this is 1819, but this is, I have underlined exactly the same sentence that featured in the 1822 treaty. So this is exactly the same paragraph, as I will confirm when I project the next slide. So just as one has names to express the various modes of existence that one wants to compare, one must also have names to express the various modes of non-existence in order to give both accuracy and precision to the language of geometric reasoning. This is exactly the sentence that he will copy 4 years later in the treatise. But now, instead of introducing the metaphysical entities that he wants, he writes, the metaphysical notions themselves have their true source in the perseverance to apply the idea of continuity to a purely ideal state of a system. Ideal, again, in the ancient meaning of ideal, and to extend to it conception and laws that belong only to the primitive state of the system, which was real. From this idea, one can see how we could go about tracing a faithful and complete table of all the metaphysical notions that belong to the figure magnitude. My intention is not to undertake this table. It would require more boldness and talent than I possess to dare deliver such a work to the judgment of the severe criticism of geometers. It will suffice for me to have indicated to those more skillful than I am the road that must be followed. And this metaphysical program seems to be fulfilled by the presentation of this these ideas about modes of non-existence and modes of existence in the 1822 treaties. So this is why I assert that it's a combination of philosophical and mathematical reflections that led Poncelet to introduce ideal elements as opposed to imaginary elements into geometry, a move that was embraced by Kummer, who carried out exactly the same move using ideal and not imaginary in number theory. Thank you very much.
Thank you so much. Now we have some time for questions. Yes, please.
Lovely. I wonder if you could comment on, there's a passage in Hilbert's paper on the interest where he says that he's using ideal in the sense of a Kantian regulated idea. And so the distinction there that he's drawing between what he calls conventional mathematics and infinitary mathematics is roughly corresponding to the Kantian distinction between constitutive and regular. I see something like this going on with Poncelet as well.
So, in fact, you have put your finger on part of the project that we have with Bruno, because in fact, there are references to Kant in Poncelet's letters, in Poncelet's manuscript. He refers to him as the geometer from beyond the Rhine. So you cannot find Kant directly, but he is mentioned. And in fact, he belongs to a circle of people who, in which we find Servois, for instance. And Servois wrote a pamphlet against Kant. So there is a whole debate at the time between these geometers, between the who are also working on analysis. There is a debate that is against Kant, but we have not yet figured out exactly what is exactly the debate about. So unfortunately, next time I give a talk, I will return with Bruno to this question. But the only thing I can tell you is that Kant is there in the background. And that Poncelet, Sarvois was a teacher of Poncelet in high school. And then Sarvois kept working on analysis and geometry, published a book in geometry. When Poncelet wrote the fourth notebook from which I have quoted, he sends it to 3 people, among whom Sarvois, precisely. So this is a very interesting question, but for the moment I do not have, but it adds to the claim that Poncelet is really working on philosophy, and he is not the only one. He's not the only one among the people who are working on geometry. So just wait a little bit for a precise answer to this question.
Yes, I'm sure that you will scandalize what I will say.
Go ahead.
It is a clear example of one fact.
Yeah.
Very often, in philosophy, trying to interact. Very often, philosophers try to interact with mathematics, a lot of stupidity, and sometimes mathematicians try to make philosophy inside a lot of stupidity. And you say to me, what Conqueror say is simply without instance. It's simple. There is no science in which a philosopher can understand the precise non-existence, imagination, there's no it's a mess. It's intense. In any case, existence in which sense? We are speaking of the existence in the world, or we are speaking of arrivability within the mathematical field. So if this existence in the world, I would like to compare it with that. Explain to me what you mean by existence in the world of a mathematical. Otherwise, we are simply empty words. If we speak about I am not
Okay.
Within a mathematical theory, so exists possibility. So I think that what Poncelet wants to say is there is 2 different objects, and there are sort of objects that are not constructible for different reasons. There is one that was not constructible to depend on a certain reason, other for which they want constructible to depend on a certain reason. So what I would like to understand is what is not constructibility. If it is not constructibility, but it's not external existence, so what is the sort of internal existence? That's really, I do not understand.
You cannot say that someone is writing a mess without having read this person. You can say, having read this person. And I can tell you that Poncelet, no, you read, okay, wait a minute. I'm going to deal with this gentleman. Okay, I have a question for you before I answer. Has it already happened that you told a colleague who was presenting, this is a mess, you have not defined this, you have not, has it already happened? It's a question. Have you already gone up when a colleague was presenting to tell this person, this is a mess? Okay, so, okay, fine. Does that mean that this person was not a philosopher?
No.
Okay, so point taken. So it's not you who can judge everybody, but it's different approaches, different constructions that can be appreciated, and they have to be appreciated in the text and not through Excel. So I've tried to give you an idea of an entanglement and of the fact that Poncelet perceived of his own program as metaphysical. Whether you think it's a mess or whatever, this is his own perception of what he's doing. Okay, now, all the questions you have, you write them down, and we try to see if we can answer these questions. But what you are doing is you are reading objects, with a modern meaning of object. You are reading Poncelet from the perspective of a modern program on mathematical objects, which is not, when you say existence, what does that mean, existence, and so on, which is not what you should do with him. What you should do with him is try to understand what his metaphysical search has done for his mathematics.
This is what I am to do, working with bioeducation technology, which is
So, as I explained, I repeat, an imaginary, a line you can define using a point and a direction. If you have no real point and no real direction, the line is not constructible. And this is an imaginary line. If you have existence is in this case, no, wait a minute. Non-existence is divided into two cases, imaginary and ideal. You can construct something that has imaginary components, like an ideal chord. The ideal chord is the chord that goes through the point M prime and N prime. These points are imaginary, okay? So this line goes through two imaginary points, but we know that it has a real point whose existence does not depend on M prime and N prime. And we know its direction, which is the direction conjugate to the diameter. So we can construct this line, but that does not mean that this line exists. It is ideal in the sun. No, wait a minute. Wait a minute. You can construct this line. I just made something imprecise, so I reformulate what I said. It is an ideal second. Namely, it is a second that I can construct, but its relation to the ellipse is imaginary in the sense that its relation to the ellipse is embodied by the points M prime and N prime, which are imaginary. So this second is a second. I can construct it, but I cannot construct its imaginary intersection with the ellipse.
The mathematical explanation is clear. I'm not saying that Poncelet is not a good mathematician. The mathematics is clear. The problem
mathematics is clear. We will invite you to read with us. We will invite you to read with us.
That the things that philosophical languages of existence, of an existence, of metaphysics, etc. You think that when I see mathematics, I understand what I'm working.
I promise to you that if you read Poncelet, you would not be.
So it's not the question to us. The mathematical point is clear.
No, it's clear because I have explained it to you. It's clear because I have explained it to you.
It's not that. In any case, that's the problem. Is what is this philosophical language?
The fact is, Marco, that this philosophical language has given Kummer to think and to find ways of introducing ideal divisors. Yes, it's absolutely, you can say no, you can doubt, but this is what is written here. This is what is written here. You have the German and you have the... No, what I'm saying to you is that the concept of ideal was influential for Kummer. This is what I'm telling you. That's what I'm... and this, excuse me, but this concept of ideal, it derives from a reflection to distinguish among different ways of non-existence.
That is what I think. That is exactly what I think.
Eric, please.
This is not to indicate.
Oh,
I have a small question. Maybe this is common, but is the idea that a finger is a system? Was that a standard view?
so this is a view that emerged at the end of the 19th century and beginning of 19th century, I would argue. So this is a view that, in my view, Poncelet, for instance, finds in someone he read a lot, namely Lazare Carnot, who is already deforming figures by continuous motion and so on. So this is something, this is the first step to take to change the notion of figure. And Poncelet, in his introduction to his treatise, makes clear that he doesn't want to use the figure of ancient geometry on which you can simply do reasoning on what you see, but he wants to promote a new idea of figure. So Poncelet's figure is not exactly the same as Lazare Carnot's figure. This has not yet been fully analyzed, but there is among Monge, Lazare, there are figures that are systems composed of parts.
Are they reading Lambert or Lambert?
Poncelet refers to Lambert, yes.
Because I wonder if he is also figure in this particular background.
This is not a main figure. There are occasional reference to Lambert, but this is not a main figure. Thank you.
Question. I mean, we have time for a last short question, please.
Thank you very much. I understand better the concept of tumor extension after the fall.
Thank you.
Tumor extension in the black matter theory. I would like to know what is exactly the influence of Pascal on the work of Poncelet, because some theorems of Poncelet degenerate some directions with Pascal.
Yeah. So Poncelet read Pascal. Some manuscripts by Pascal were found and published at the end of the 18th century. So Poncelet certainly read Pascal and he refers to him. And in particular, he's interested in what he reads in a treatise of Pascal that is lost, but about which we have notes by Leibniz, which is a certain kind of generality that when you can identify a property, and this is the famous mystical hexagram, you can identify a property through which, by simple proof, you can obtain many 400, he claims, properties that Pascal had brought under the umbrella of a single theorem. So this is a construction, a geometrical construction that is comparable with the construction that had been made with analysis in the 18th century. So Pascal is certainly someone that he read since he was at the École Polytechnique.
Well, thank you so much, Karine. It has been a very nice and interesting talk. I
Thank you.
always knew that Kumer came up with this idea of ideal, and we are referred to it, but I didn't know that it was so deeply rooted in geometry, and it has been really very interesting.
Thank you. Thank you.
Learn that from you. So thank you again to our speaker.